Okay, Christian.
Yeah.
Juju Bear.
Yep.
Sherilyn. Neff. Tree. Trees don't talk. Come on. Anyway. All right. So, approximating error. So, relative error at whatever my initial x is in Q. This is going to be absolute value of the change in my Q divided by the Q. We started working on this yesterday, and it was a bit frustrating, and I'll show you guys how to do this, because it's throwing in a whole bunch of stuff, and I hate throwing in stuff. That's why I hate doing this. Anyway, a company manufactures spherical ball bearings, a radius 3 centimeters. Bam. That's important, 3 centimeters. The customer requires a tolerance of no more than 1% in the radius. So, anyone understand what the tolerance means? What's that mean? Yes. So tolerance means I will only tolerate you acting like a fool to a certain point. If your foolness goes up higher than that, it's unacceptable, right? In manufacturing, that's something that they talk about for quality control. Manufacturing, not every item is going to be exactly perfect. But there is an error of tolerance where perfection is not required, but close enough is. So, that's what this is talking about. So it says use differentials, approximate the relative error for the surface area. Okay, so when I looked at this yesterday, I did volume first and then surface area. So the volume wasn't necessary, but we'll just do we'll go to the surface area because that's what the tolerance is talking to. So of the surface area, I have my tolerance, which it's going to be, I have R is 3 centimeters, and my tolerance is 1%. My tolerance is 1%. So 1% of that's 3 centimeters. The stupid thing just opened up windows everywhere. Okay. So 1% of that 3 centimeters. What is 1% of that 3 centimeters? So it is going to be my 3 times my 1% as a decimal, which will be 0.01. That's 1% as a decimal, right? Okay, you could also do it as a fraction if you want to, which would be 3 times 1 over 100 is 1% also, but as a decimal it's right there. So this is probably going to be the more helpful way of actually doing it, because you might actually have to do some weird decimal type of wait, no, sorry. Anyway, so there we go. So 3 times the fraction, because if you have to do a 2.5%, it's a little bit easier to try and do it like that. 2.5 divided by 100, because a lot of people screw up that fraction portion all the time. So right there, I get this comes out to be 0.03. So that is my tolerance. And this is going to be my centimeters. And this is going to be the plus or minus, because the word tolerance doesn't always mean it's going to be less than. It could be greater than also. So plus or minus that. So that's important when we're actually talking about this. So there's my tolerance right there. Now I'm going to go through and I'm going to do my volume. I'm sorry, not my volume, my surface area. So my area, let me change colors so I can. So area is equal to 4 pi r squared. So this is the area of a sphere. Area of a sphere. So I'm going to take the derivative of that. So take the derivative of that is going to be dA dr, because I'm taking the derivative in terms of the r. R is my variable there. Equals, derivative is going to be 8 pi r, 8 pi r, and then what we learned the other day when we were actually trying to get my delta A, my dA by itself. If I'm looking to get my dA by itself, I'm going to multiply both sides of this problem by delta r. So multiply everything by dr. There you go. So I multiplied both sides by dr, and then I'm going to cancel it out from the left side. So now I'm going to have my delta A is equal to 8 pi r times dr. Now, I'm going to go back in my formula a little bit. Back in my formula said that I have, it is absolute value of my delta A divided by my A. I believe it said it said it in Q's, didn't it? That's what it was referring to. Okay? So, it is my delta A, that's the change in area. By doing that, it's a change in area. So I'm going to use my two formulas that I have, which is my delta A, which came out to be 8 pi r times dr, divided by 4 pi r squared. So that was the whole purpose of doing that Q, absolute value of delta Q, and divided by Q of x sub naught, right? Does that make sense? No? Maybe? Okay. Now we know what these items are. So delta A is a change in A. My dA is a change in A. R, what is the R value? R value wasn't it 3? R value was 3. What else did I have? I also have my dr. Now, delta R, dr, did I find the change in the radius? That was the first thing I did. That was the tolerance. So the change in radius was how much? 0.03? Like that? Okay, good. So now it's an algebra problem. Now I'm just going to plug in what I have here. So it's going to be 8 pi 3 times 0.03 divided by 4 pi 3 squared. And let's go ahead and plug this in my handy dandy calculator. Oh, thank you, calculator, for jumping up for me. smartboard here? There we go. Alright. Scratch pad here, control, divide. It was 8 pi, right? Times 3 times 0.03 divided by 4 pi times 3 squared. And we should get, there we go. So that's going to give me the surface area I'm allowed. So that is my surface area I'm allowed to actually be off. So my whole thing has to be less than, because if we go back to the problem, all this right here has to be less than I hate drawing with the mouse. Less than equal to 0, angry face again. 0.02 So that's my tolerance on my area. It's got to be less than that. The surface area of the volume. Now, to do the last part, which is going to ask for the percentages, I take my dA, absolute value of dA, divided by A, and then times 100%, which is going to give me 2% of my entirety thing. That's the error I'm allowed. You know what's sad? My other classroom, I just got a brand new smartboard because my other smartboard was doing this. And then I moved to here, and guess what? The smartboard is doing this. So I guess I need to go steal another smartboard from somebody. But you ain't heard it from me. I'm not saying that I'm going to steal it. I'm not saying I'm recording the fact that I'm going to steal it. I'm just saying, it is not in use at this current moment in time that someone with some hand tools and some know-how could probably get this thing fixed. It just annoys the crap out of me, sorry. Anyway, so let's go ahead and do some Newton's method. So we're going to do a bit of Newton's method now. So, Newton's method for approximating real zeros of a function. Suppose a function f is defined on a closed interval. That means that it is equal to both ends. Okay, bracket on both ends. That means I could use that. It is defined, so I don't have any holes, I don't have any undefined, I don't have any skips or anything in that area. So in between those two in my domain, it all must be real. And it's the first derivative f is continuous and not equal to 0. So what does that mean if it's continuous and not equal to 0? Think about derivative. What does a derivative give me? The slope, right? Basically, it's the slope of a line. So it's slope of a tangent line, right? So it is continuous. That means I don't have any places in which that my slope is undefined. I'm not going to have any weird cusp or anything. And is not equal to 0. So 0, it would be no change, right? Through the entire thing. But if it was positive slope, it would go like this, right? So on my number line, if it's positive, my slope somewhere in between should start off at negative as I plug in my numbers, and it should change to positive, right? So somewhere in there, it's going to cross through 0. We're using intermediate value theorem along with this. So my numbers, my f values, f of x, is going to go from a negative to a positive if my slope is positive. If my slope is negative, and I'm reading from left to right, my f value should start off being positive and end at negative, right? So that's what that means. So if x is equal to c1 is sufficiently close to the first approximation to a real zero of a function f in a to b, then the formula right here, okay, this is important, gives the second approximation to the 0. The nth approximation to the 0 is given by this formula here. So, you have those written down? Most likely somewhere, right? Good. So, let's see if I could actually do this one here. Use new method to find the fourth approximation to the positive real zero of the function. That means that my values are going to go from negative to positive. It's going to go from negative to positive in an interval. I got to find what that interval is first. Where is it changing from negative to positive? So I could try and do it mentally. We're going to just use integers for this. So starting with integers, if I plug in 0, so f of 0, f of 0, so you guys are going to help me read this so I get it right. F of 0, so it was it x squared or x to the x cubed? Okay, so let's do this here because we're going to need this several times. X cubed Do you remember why we do this here, put this here first? Because we're going to use our vars function for this one. Enter. Okay. So we're doing a little bit of cheating right here, but I'll show you how this works. So I know it's not here at 0, but it's going to be somewhere between 1 and 2. So it's going from a negative to a positive right here in between 1 and 2. We're trying to approximate this 0. So this is closer to 1 than it is to 2, right? That's going to be important. So using vars, we say f of 1 gives me -1. F of 2 gives me 8. So I know it's going to be between. So my function is going to cross the x-axis in between -1 and 8. So we're going to approximate by saying, is it closer to the -1 or closer to the 8? So if I want to give it a decimal, what would my decimal be? The better you guess on this first one, the easier it makes the rest of this. Because we could just jump to the middle, 1.5, but why not 1.2? We could check it at 1.2, right? Okay. So same thing, but we need to use that function equation here, right there. So I'm going to do f of 1.2 right here. So this is 1.2 minus f of 1.2 divided by the derivative at 1.2. So I have to find the derivative also. So let's go to the next page. The derivative, let's see if the derivative will work now. So f prime of this is going to be 3x squared plus x minus 1. And that's what I'm going to plug into my second function. Go here, tab, there's my f2, 3x squared minus 2x, was it minus 2? Oh, plus x plus 2, yeah, I should have a 2 here, thank you. Plus 2x minus 1. There you go. So I need both of these here. Both these are going to help me out. My function, so we're going to try the function. So we said 1.2, right? So it's 1.2 minus, control divide, f of 1.2 divided by the derivative at 1.2. Is that a positive number? Because I want the closest number that's going to be positive, right? That's what the instruction said. I wanted a positive real number close to 0. I can get this thing closer to 0, can I? Okay. So what I'm going to use is, I'm going to use the previous, and I'm going to use this number here to actually get closer to the next one. So by doing the iterations, I take the previous number and I plug that in for this. So I'm going to take this number let's round it. control, divide, f of that number divided by f prime of that number. So this one gives me the second. The second iteration of this. And then I keep doing this, and it's asking for which one? Okay, find a fourth approximation to the positive real zero of the function. Okay, so now, since we started with really close, that was actually a pretty good answer. So since we started with 1.2, it was really close to my answer. So let's look at it again. And so if I was to round this right here, the only thing that changed is the 9 at the end. So this one was the second minus control divide this one right here is going to make it the third. Now what happened here? As I rounded it, what happened? If I were to round this one right here, do I get the same number? So the closer and closer I get, I could keep getting the same number. So that means that should be my answer. So from my third, if I can get the same number as my second and my third, guess what the number is probably going to be on my fourth? The same thing, right? So I'm going to show you by plugging in the entire answer. And let's go to the graph, 1.20557. Menu, analyze graph, 0. I want on this one, in between here and here. So what we're actually doing is using Newton's method. We're finding the 0, which we could have just used the calculator and spent the last 45 minutes working on this one problem. That's my angst. I've yet to actually find a real reason to actually do Newton's method versus just throwing in the calculator and getting the point on the graph. Are you going to really try and find the derivative, plug in 1.056? You're going to plug that in anyway, right? You're going to plug that in anyway, so because your function at that number divided by the derivative at that number is just super gonna suck, right? So Newton's method is in replace of having a graphing calculator. So back in Newton's day, he didn't have any graphing calculators. He should have spent more time and invented that instead. Because Leibniz invented calculus, Newton should have created the graphing calculator. Yes, and he did this by hand, so I hate the guy for that. Anyway, so right here, intermediate value theorem confirmed that this has a 0 in between here. Use the graph of the function. We can graph this here, right? And you guys hopefully are not falling asleep. We should have a 0 in between there. Graphing technology, Newton's method, to find here, to find a fourth of this. For graphing it anyway, we're going to find this anyway. So, my angst about having to do Newton's method is going to consist of, throw it in a calculator. Tell me what the answer is. I taught you how to do the Newton's method. Wink, wink. As long as you guys can still get the answer, wink, wink, wink. Right? Okay. And just so you know, the actual answer in the Newton's method, because Newton's method is an approximation, it's going to be slightly off, but we round it to what decimal anyway? Third decimal. So Newton's method will get us down to a third decimal in most cases. So when does Newton's methods not work? Whenever I don't have a calculator. There you go. Make sure you guys all like, share, and subscribe. I need to go steal a better smartboard.